Test everybody. So before I start today's topic, I would like to have a little recapitulation about last class topic, that is resonance. So I would say that we discussed that at resonance, that is at omega is equal to omega naught, that is at resonant frequency, that is at resonance, we say that Xc is equal to XL. That means resistance of entire circuit is equal to Z is equal to R. That is Z is equal to R. That is impedance. Total impedance become Z is equal to R under a condition that Xc is equal to XL. So we normally say that Z is equal to root of R square plus Xc minus XL whole square. So if Xc is equal to XL, then Z is equal to R, then amplitude of currents would be a maximum, right? This is what we call as maximum amplitude of current. This is what we call as maximum amplitude of currents. So we say that a maximum amplitude of current would be Vn divided by R. Why? Because here in this case Z is equal to R. Alright, so this is what we call as resonance. So this is going to be, and then we will be having a different peak for a different resistance. If a resistance is low, peak is going to be higher. If a resistance is higher, peak is going to be lower, right? So this is what we talked about last class. All right. So today, what I'm going to do is I would like to discuss the sharpness of resonance. So we would like to study the resonance, right? So this is what we call as sharpness of resonance. So this is last class. So having this now, so at resonance for a different resistance we would be getting a different peak. All right. So this is R1. R1 is going to be less, so therefore peak is higher. R2 is going to be more, therefore peak is going to be lower. So this is what we have. Now I would like to do today's topic, that is sharpness of resonance. So we have learned that amplitude of current in a LCR circuit is going to be Vn divided by root of R square plus Xc minus XL whole square. This is what we have. This is what we have in case of in case of amplitude of current in LCR circuit. In LCR circuit, right? In LCR circuit, that is, and I can rewrite this equation, and I can write this, nothing wrong if I write R square plus XL minus XC whole square, right? Why? Because since it is a whole square, it doesn't make any difference. So this is what we have last class, and this is the amplitude of current, right? This is amplitude of current. This is amplitude of current. This is amplitude of a current in LCR circuit. In LCR circuit. All right. So now we will say that Xc is going to be 1 by omega c. XL is equal to omega L. This is the formula. We've done it. And now what I would like to do is, now at resonance, that just now I talked about, at resonance Xc is equal to XL. At resonance omega is equal to omega naught, where omega naught is equal to 1 by root of Lc, or omega square is equal to 1 by. Alright, at resonance omega is equal to omega naught, alright, and omega square is equal to 1 by LC's, and then amplitude of current is going to be a maximum amplitude of current, right? This is what we call as maximum amplitude of currents. This is what we call as maximum amplitude of currents, which is equal to VMR, which is equal to VMR. So this is what we have, right? This is at peak. This is what we have in case of a peak. So we talk about this. This is going to be at this omega is equal to omega naught. All right. Now what we would like to study is I would like to choose a two frequency, right? So let's say I'm going to choose this. This is a frequency 2. I would like to choose this. This is frequency 1. And at frequency 1 and frequency 2s, we would say that the current amplitude of current is going to be just square root, right? So this is what we have. So I just say that this is at resonance. Now I just choose a two frequency at omega is equal to omega 1s, where omega 1 is equal to omega naught plus delta omegas, and omega is equal to omega naught omega 2 is equal to omega naught delta omega. All right. At this two frequency, I say that amplitude of current would be equal to this is what we choose, right? So I choose these two frequencies, and this is very, very important, right? So we'll be having a same amplitude of current at a two different frequency, right? At a two different frequency. This is what we have, and then I say that omega 1 minus omega 2. This is equal. This is the width, right? This is going to be this, and this is equal to 2 delta omega. So this width is going to be 2 delta omega. This is what we have, and this is what we call as a bandwidth. This is what we call as bandwidth. This is what we call as bandwidth. This is what we call as a bandwidth. This is what we call as bandwidth. Now what I would like to study is this bandwidth, right? If I keep this very sharp, then this is going to be sharpness of resonance is high, and if I keep this little wide, then the sharpness is less. So I would like to define a physical quantity called a sharpness of resonance, right? So I would like to define something called a sharpness of resonance. Sharpness of resonance. I would like to define something called a sharpness of resonance, which is defined as delta omega naught. So this is what we call as a sharpness of resonance. I define a physical quantity called omega naught divided by 2 delta omega, such that this defines the sharpness of resonance. This defines the sharpness of resonance. This is going to define a sharpness of resonance. So we would like to find out such that which physical quantity, that is capacitors, capacitance, inductor, resistors, right? How this quantity depend on these factors, right? So this says that if bandwidth is smaller, then sharpness of resonance is going to be more, right? If bandwidth is wider, then sharpness of resonance is going to be less. So this is what we would like to study. All right. So now what I would like to do is, all right, I'll take this. Now I would like to take omega naught, omega 1s. So I say that at omega is equal to omega 1, which is equal to omega naught plus delta omega. All right. So what I would like to do is, this is equal to M is equal to Vm divided by Z. All right, Z, which is equal to let's say I would like to do like this, right? Which is equal to I am max divided by root 2, right? All right, this is point, right? And having this I say that I am max divided by root 2 is equal to Vmz. All right. So having this, what I would like to do is, I'll write here. Yeah, I'll write here. What is Imz? This I'll rewrite this. Vmz. So this is going to be Vm root 2 r, which is equal to, this is equal to Vm's r square plus xc, right? Omega L, omega 1L minus 1 by omega CL whole square. So this is what we have. Alright, so I just cancel out these two. Once I cancel out these two, r square plus omega 1L minus 1 by omega, this is C, alright, this is 1, omega 1 C whole square is equal to root 2 r. Alright, this is what we have. This is what we have. I will put the square root. I have to put square root. And squaring both sides, if I square both sides, squaring both sides, I get this. Actually, this is some algebraic step 2r. When I put this 2r, alright, when I put this 2r, r square is there, I'm sorry, and then omega 1L minus 1 by omega 1C square is equal to r square, square cancel out, alright, square cancel out. Again, I will step one more step, I will write r, right? Okay, now I would like to substitute this. This is equal to omega 1 omega naught plus delta omega L minus 1 by C omega naught plus delta omega equal to r. Okay, now I just take common out 1 plus delta omega L minus this is equal to C omega naught 1 plus delta omega naught equal to r. So this is a simplification. I'm doing it, and then now what I'm going to do is this omega naught 1 plus delta omega naught, okay, L minus, okay. So what I would like to do here is omega square is equal to 1 by LC. This is what we have done, right? And 1 by C is going to be what? 1 by C is going to be omega naught square L. Alright, I substitute here omega naught square L divided by, alright, omega naught, and then I'm going to put it inverse. Alright, this is what I do, and then these two cancel out, and again I'm doing one approximation, right? The approximation is that since delta omega divided by omega naught is much less than 1, then 1 plus delta omega naught whole power minus 1 is going to be 1 minus, this is approximation, right? This is approximation, and you don't need to know how this how we are going to get this. This is simply approximation. You might have done in class 11, right? So now substituting this, we would get omega naught 1 plus delta omega naught L minus omega naught L 1 minus delta omega naught equal to R. Alright. So now omega naught cancel out, okay, and then what we are going to get is 2 delta omega L divided by 2 delta omega L, and then omega, let's say I'll do like this, 2 omega naught delta omega L divided by omega, which is equal to R. So this is the formula, we got it, and now we would like to figure out formula in this term. This defines the sharpness of resonance, right? So defining sharpness of resonance, we define the sharpness of resonance. What is that sharpness of resonance? Omega naught delta C, right? So I would like to figure out this, right? So we would write this omega naught divided by 2 delta omega. This would be equal. So maybe for your better understanding, I just write this. This is equal to omega naught L, which is equal to divided by R, omega naught L divided by R, which is equal to omega naught divided by 2 delta omega. Alright. So what is 2 delta omega? 2 delta omega is going to be sharpness of, this is going to be a sharpness of resonance, right? This is going to be a sharpness of resonance, right? So I just say the sharpness of resonance, that is omega divided by 2 delta omega, is going to be omega naught L divided by R. So therefore the sharpness of resonance is defined by this quantity, and therefore since the sharpness of resonance is defined by this quantity, therefore we call this as a quality factors, right? This is what we call as quality factor, right? This is what we call as a quality factors. So we say that quality factor Q is going to be omega naught L divided by R. Omega naught L divided by R is going to be a quality factor, right? This is going to be a quality factors. So the sharpness of resonance is defined by L as well as R. So this is what we are. So this is what we term as a quality factors. This is what we call as a quality factors. This is one. And then I say sharpness of resonance is entirely defined by a bandwidth. So smaller the bandwidth, greater would be quality factors. This is the point. And now I would like to figure out in terms of a capacitance, right? So in terms of capacitance, I say L is going to be 1 by omega naught square C, right? This is L. Alright. Having this, I substitute L. Having substituted L, I say Q is going to be omega naught divided by R, omega naught square. C cancel out 1 by omega naught RC. 1 by omega naught RC. Alright, so in terms of capacitance, quality factor is defined by 1 by omega naught RC. In terms of capacitance, quality factor is defined by 1 by omega naught RC. So this is why this is very important is that if the quality factor is better, the sharpness is going to be a better, right? Sharpness is going to be a better. If a sharpness is going to be a better, if this is the sharpness of resonance, so whichever frequency falls within this bandwidth, you would get a maximum currents and you would get a maximum signal, right? So if this bandwidth is bigger, if this bandwidth is wide enough, then so many frequency falls within this bandwidth, and we would get so many signals at a time. And this is not a good thing, right? So we need particular signals at particular bandwidth, right? So therefore, we would say, so if I choose a very thin bandwidth, so only particular signal falls within this bandwidth, so we would get more current, more signal. So this is the idea behind this, right? So this is all about sharpness of resonance. Right? All right. So this is what I have written.